So okay, we have discussed about upflow anaerobic sludge blanket reactor in the last class. So in upflow anaerobic sludge blanket reactor,
Sir,
we get yes.
sir,
Go
in
ahead.
last class you mentioned about that class presentation like a will be like 40 marks to 60 marks. So about that you told that we will be discussing. If you can clarify.
That we can discuss at the end of the class. Okay.
Yes, sir. Thank you, sir.
Okay. So in USB, mostly we get influent from the bottom of the reactor, and at the top we'll have a three-phase separator where gas, solid, and liquid will get separated, and liquid, gas, and solid will actually move through different channels. So if you can remember, in between the cone and this uh, notch of this particular reactor system, only liquid will go out and all solid will get arrested on the cone, and they will again come back to the liquid system due to gravity, and gas will get collected at the top, and through the gas vent it can again either get collected in a big balloon, or we can have gas supply line to just use that gas elsewhere. So typically in anaerobic treatment system, we use a gas polishing unit because the microbes present in the system will not only have methanogens, it will also have sulfate reducing bacteria. So sulfate reducing bacteria and methanogens, they compete for similar substrate. So one class of methanogens utilizes acetic acid, and SRB also utilize acetic acid for as carbon source. So whenever you have this kind of system where sulfate content or sulfate content is significantly high, there you will get dominance of SRB. So one of the primary reason is SRB, their growth rate is much faster than methanogens. So when you will have this kind of substrate like sulfate and acetate, because for growth of SRB, sulfate is also required and acetate is also required. So whenever you have sulfate and acetate at a specific concentration, SRB will try to dominate the system. And sometimes this overpowering methanogens actually destroy the anaerobic reactor. Destroy means you will actually get failure of the anaerobic reactor because methanogens will not be able to sustain. Mostly SRB will dominate the entire reactor and they will produce lot of H2S. So H2S is undesired product in system because this H2S can create microbially induced corrosion. So whenever you have H2S in the gaseous stream, if you burn the gas, suppose in an anaerobic digester, you are getting from the outlet, you are getting biogas. Biogas means mostly methane, certain amount of carbon dioxide, little bit of hydrogen, and also H2S. Now, when you burn it, obviously you will get certain calorific value from methane because methane will get converted to carbon dioxide when you burn it in presence of oxygen, and you will get energy also. Same thing will happen with hydrogen also. Now for H2S particularly, it will get converted to sulfur trioxide, and in presence of moisture, the sulfur trioxide will get converted to sulfuric acid. And sulfuric acid is a strong mineral acid, and that acid will actually create corrosion. So whatever reactor vessel you have, whatever pipeline you are using for transporting this gases, that entire environment will get polluted by this H2SO4, and you will get microbially induced corrosion in that region. Now, question is, obviously H2S is not undesired, not a desired product, and when you have H2S, it will also reduce the overall calorific value of the gases, because you are not going to get any energy generated by burning H2S or by oxidizing H2S. So overall calorific value will get reduced, and also you will have problem with microbially induced corrosion. So to avoid getting all this hassle of H2S, one option is to maintain methanogens dominated system, and that dominance can be obtained by having very low sulfate concentration in the system. So whatever effluent you are getting, you have very minimal control to manipulate that effluent. So if you are getting certain amount of sulfate, you don't have any option to remove sulfate from the influent or wastewater. Only thing is, you have to make sure the sulfate COD sulfate ratio. COD means chemical oxygen demand. That actually signifies how much oxidizable carbon present in the reactor or in the influent or wastewater. So COD sulfate ratio, if it is less than 0.67, then it will have dominance of SRB. That means you have higher amount of sulfate compared to chemically oxidized, means this COD value or chemical oxygen demand. So chemical oxygen demand is actually talking about carbon content present in the system, which is oxidizable and which will give you certain amount of carbon dioxide. So chemically, when you try to oxidize any compound present in the system, then you can estimate the oxygen demand or chemical oxygen demand of that influent. So generally for COD estimation, we use strong oxidant like potassium dichromate, and then we oxidize the oxidizable content present in the liquid, and finally from this reaction, means potassium dichromate plus means K2Cr2O7 plus your wastewater will essentially have carbon, will get carbon dioxide. So this potassium dichromate, in this reaction, how much amount of oxygen is actually required for oxidizing all carbon will be estimated, and that value will actually give you chemical oxygen demand. So essentially, chemical oxygen demand is actually talking about oxidizable carbon present in the system. And also we have another term called biological oxygen demand. So all chemically oxidizable compound may not be biologically degradable. So in a given wastewater system, whenever you collect wastewater, you do this analysis, you actually do chemical oxygen demand analysis, you also do biochemical oxygen demand, and biochemical oxygen demand will actually give you absolute idea about the biodegradable component present in the wastewater, whereas chemical oxygen demand will give you idea about oxidizable compound present in the wastewater. Now, in a wastewater, whenever you get this COD value, and COD value you can estimate experimentally. Similarly, BOD value also you can estimate experimentally. Now, experimentally, yeah.
BOD value will always be greater than BOD?
Yes, that's all. That's the case, but in some cases you can actually get equal value also. Suppose you are having glucose solution, and in the solution you don't have any other component. So you know glucose is completely biodegradable. So whatever BOD value you will get exact similar value of COD also. So it depends on the constituent. So most of the cases COD is more than BOD, but in some cases you can get BOD equal to COD, but BOD will never be greater than COD.
Yes, sir.
Yeah. Now, when you estimate the COD, you can get value because generally we express it in milligram per liter. Because here we actually estimate how much oxygen is required for completely oxidizing that compound. Like if you have glucose, now you add oxygen. See, this oxygen is actually coming from dichromate, and then you convert it to carbon dioxide and H2O. So you know how much oxygen is required to convert it or to oxidize completely to carbon dioxide. So from this equation, we know it is 180 gram, the molecular weight, and how much oxygen is required. 6 into 32. So that is the amount of oxygen required.
Yes.
Just a second. So it is 192. So when you try to calculate COD, so 180 gram glucose would need 192 gram O2. Fine. So 1 gram glucose will require 192 by 180.
180.
So whatever value you will get, it will come somewhere around 1.66. So this value is actually chemical oxygen demand of glucose.
1.066.
Okay, fine. 1.066. Fine. 1.066. So that is, so it is gram O2. Now, if you do it in liter, suppose you have this in 1 liter liquid, then actually you can calculate this many gram per liter is required for 1 gram per liter glucose. If you put it 1 gram per liter or 1 gram per liter, then it will also 1 gram per liter. Here also then 1 gram per liter. So COD calculation you can do if you know the complete stoichiometric reaction, and then you can just balance the reaction and calculate amount of oxygen required. That will give you amount of COD. Now, experimentally also you can do this. So experimentally, when you do this, you just use certain amount of potassium dichromate, and you know amount of potassium dichromate you have used before starting this oxidation reaction. So you put in a you put the potassium dichromate as well as wastewater, certain amount of wastewater in a round bottom flask. Then you raise the temperature to say 200 degrees centigrade. Digest the sample, means do the complete the oxidation reaction for 1 hour, and after 1 hour, you then again check the residual dichromate concentration. So the initial minus residual will give you spent dichromate concentration, and from there you can calculate amount of oxygen present in that spent dichromate, and that oxygen actually got utilized for complete oxidation. So then you can get the concentration value, and that will give you the COD value. And sulfate concentration you can measure using again either titrometric method or by ion chromatograph. So you can get absolute concentration of sulfate. So you just take the ratio. If the ratio value comes greater than 6.67, then it will be dominated by methanogens, because that means COD is higher than the sulfate. And if the ratio value comes less than 0.67, then you will get overdominance of SRB. So in a typical anaerobic digester, if you want to get rid of the nuisance of H2S, one option is to check sulfate and COD content. And after checking that, if you feel COD is actually not appropriate, suppose COD content is little low, then you can actually add some other wastewater having more carbon content. So that wastewater, the secondary wastewater, will actually compensate and increase the COD value, and then make it favorable for methanogens, and you will get higher concentration of methane and less concentration of H2S. Now, even if you get certain
Sir?
amount of H2S, yeah, go ahead.
In case of wastewater treatment plant, we need to increase the BOD value or COD value. Like, what is
Yeah,
exactly?
obviously, it is BOD only, but COD, BOD, there they have certain relation. As I told you, BOD will be certain fraction of COD. BOD could be 1, means the fraction value. So it is like BOD. So this F value could be 1 or less than 1.
Sir, to determine the BOD, do we have like a standard or microorganism, or do we
Okay.
determine?
Yes. So for determining BOD, you just uh, put the wastewater sample, taking different volume, and sometimes you add small amount of bacteria, and then you keep them at certain temperature. Means you can do at 25 degree centigrade temperature, or you can do at 27 degree centigrade temperature, and then you incubate them for certain period, 5 days or 3 days. Now, after 5 days, so before starting the experiment, you estimate the oxygen present in the bottle in the water, or oxygen content in the water, because you are not supplying any extra oxygen from outside, and the inoculum you add, they are all aerobic. So in the liquid, whatever oxygen is present, that will be utilized by the bacteria to degrade the carbon. So before starting the incubation, measure the oxygen content, and then after end of the experiment, like after 5 days or 3 days, you again monitor the oxygen concentration in the liquid, and difference will actually give you the spent oxygen concentration, and that spent oxygen concentration will signify the BOD value. So if it is readily degradable or biologically degradable, then you will get higher value of BOD. So that's why the fraction F value could be 1, and or maybe the F value would be a little bit less than 1. Now, for any wastewater, when you get any wastewater, you first characterize, means you just do all this analysis, different ion analysis, oxygen, the BOD value, COD value, nitrogen content, sulfate content, different other ions are also there, and then you just get some sort of idea of this ratio, BOD COD ratio.
Sir, my
Yes.
question was actually about BOD, that when we add microorganisms, so do we add some standard microorganism, or can we add any kind of any microorganism like E.
Yeah, there is
or
no
any
standard
other
organism.
species?
There is no standard organism present. In some cases, you don't add anything.
Yeah, sir. So in that
Indigenous
case,
organism will be indigenous.
BOD value will be different for different species, right?
Agree. But the concentration of that bacteria is not significantly high. And sometimes we prefer indigenous organism because some organism would grow in a specific system where other organism may not be able to grow. So in
Yes.
cases, most of the cases, we don't add anything. Whatever indigenous organism present in the system, that is considered as the organism present, that is considered as the inoculum.
Yes, sir.
But standardization of microbial community as inoculum is not done anywhere, and it is actually not very easy to do also.
Okay, sir.
uh, Now this BOD COD ratio will actually give you the biodegradability. Means suppose the BOD COD ratio is so you have very high BOD and very high COD and very low BOD, then it is not a very good biodegradable substance. Suppose you are getting reasonably good BOD and COD ratio, then you can say that it is a it can be treated using biological system. So when you try to use any of this biological treatment system, first thing is to estimate biodegradability. So you do assess all this parameter and then check whether it is biodegradable or not. And in anaerobic treatment system, specifically, we prefer to use wastewater where organic content is significantly high, because aerobic system uses all aerobic system will actually use a lot of oxygen. So now if you get huge amount of carbon present in the wastewater, you need to supply a lot of oxygen to oxidize that carbon. And when you try to supply oxygen, aeration cost will also increase. So that's why wherever you get industrial effluent or any other effluent having high organic content, we always try to use anaerobic system instead of aerobic system. Whereas low carbon content wastewater is preferred in aerobic treatment system, because low carbon content is easy to manage with a certain amount of aeration, and high carbon content is treated in anaerobic system. Also, wherever you have high carbon content, you will get higher methane also. That means the energy generation is much higher, so you will get more economical operation of the treatment plant if you use anaerobic treatment system. Despite of the slow growing anaerobic, still people prefer to use anaerobic reactor where you need larger footprint, larger size, and a little bit sophisticated instrumentation. Still people prefer to use anaerobic system because the process economy will actually allow you to use this kind of treatment system. Now, this COD sulfate ratio you can maintain by augmenting external carbon source. So you will get little bit, the COD sulfate ratio will be more than 0.67. Then you can actually ensure that you are not getting too much of H2S. Now, still, if you have H2S at the outlet gas, then you can have some chemical or biological scrubber. So you can have a scrubbing unit or scrubbing tower where you can have chemical, so alkali solution flowing from the top, and gas will move up. So whenever this gas and liquid will come in contact, this H2S will get used up by this alkali solution, and then finally you will get clear gases. So methane, carbon dioxide, they will not react with the alkali solution. Only H2S will react, and from the top we will get actually cleaner gases. Sometimes you use bioscrubber where some biological biofilm or bacterial biofilm will be there in the scrubber surface, and that bacterial biofilm will actually interact with the H2S to convert it to sulfur. So it will further reduce it will actually oxidize the sulfur, and then a sulfur is oxidized H2S and then convert it to sulfur, elemental sulfur. So it will also have a reduction through biofilm. But only problem is this biofilm scrubber or bio scrubbers are not very high rate system. So you get much faster conversion in chemical system than the biological scrubber. So one option is to add carbon to alter the COD sulfate ratio. Another option is to treat the gas obtained from the reactor. After getting the biogas, you just use a post-processing unit to scrap the gas, scrap the H2S. And another option is, in the system itself, you can start adding some scrap metal. So the scrap metals will actually react with H2S, and then they will form sulfate precipitate, means metal sulfide. So metal plus H2S will produce metal sulfide, and this metal sulfide will actually create precipitation, and this precipitated metal sulfide will get removed from the aqueous system, so they will not interact with the system anymore. And finally, from the reactor system, you can just remove them as sludge. So one option is COD sulfate alteration, ratio alteration. Another option is treatment of gas after getting the gas out from the gas outlet. Third option is adding
Sir,
some
this
scrap. Yes.
so this metal surface will it be able to absorb all the sulfur which is present throughout the volume of the reactor? Like sulfur will be like throughout dispersed,
Yeah.
but
Obviously, when you
metal
talk,
will be like at the bottom.
no, but for all kind of activities, whether it's alteration of sodium sulfate ratio, metal sulfate you use, or bioscrubbing, you don't get 100% removal. 100% removal is actually not possible to achieve. The surface of the water. So whenever you will put this scrap metal granules or strings, they will try to interact with most of the liquid. But it is not 100% efficient system. Neither of these systems actually. COD or scrubbing, neither of systems are actually, even this, none of the systems are 100% efficient. So the fourth option is to add some inhibitor, which is very expensive. So you can have certain inhibitor which will mimic the molecule similar to sulfate. And one of the molybdate ion is one of the candidate. So you can add sodium molybdate or some other molybdate solution, ammonium molybdate, sodium molybdate in the liquid, which will get dissolved in the liquid, and it will actually mimic the behavior of sulfate. And whenever SRB will interact with sodium molybdate, their metabolic activity will get ceased. So sodium molybdate particularly create problem with their uh, ATP synthesis or phosphate assimilation. Ultimately, this inhibitor will inhibit growth of SRB, and then you can get rid of problem of this H2S. But this addition of molybdate is very expensive compared to all other three methods. So this is at laboratory scale you can use it, but in actual real field it is rarely used, molybdate. So four different strategies I have mentioned which can be used for reduction of this H2S problem. And we are talking about H2S because it is one of the primary cause of failure of anaerobic reactor. So when you have lot of H2S production, it will inhibit methanogens also. And in anaerobic reactor, we actually get series of reactions. So anaerobic reactor, first all complex hydrocarbon will get hydrolyzed. So four different steps of reactions are happening in anaerobic reactor. One is hydrolysis, followed by acidogenesis, followed by acetogenesis, then finally methanogenesis. So hydrolysis means all larger molecules, say fat, carbohydrate, and other proteinaceous material, they will get hydrolyzed to their monomers, and then some bacteria will work on them. These bacteria are actually known as acidogens. Here it is hydrolyzing bacteria. Then acidogens. Here the bacteria are known as acetogens, and here they're known as methanogens. Now, hydrolyzing bacteria mostly they're facultative. They can survive in aerobic and anaerobic condition both. So they will use up all the oxygen while doing the hydrolysis. So then acidogens, they will produce certain volatile fatty acids like 3 carbon, 4 carbon, 5 carbon acids. So 1 to 5 carbon acids. Like acetic acid, formic acid, acetic acid, propionic acid, butyric acid, valeric acid, different volatile fatty acids they will produce, VFAs. And then another group of bacteria called acidogens, they will work on the higher carbon acids and then they will produce acetic acid. So acidogens will produce different volatile fatty acid, and from volatile fatty acid, acetogens will work and then they will produce acetic acid, and that acetic acid will be used by the methanogens. So you can see this synchronous behavior of different microbial groups will actually give you the final product. And if you have inhibition in the any of this group, suppose you are having inhibition in this step, so obviously a lot of acids will get accumulated here. If you get inhibition in this stage, you will get a lot of accumulation of hydrolyzed product. Or if you get inhibition at the end, then you will get a lot of accumulation of acetic acid. So it is known that the bacteria involved in all kind of steps like hydrolysis, acidogenesis, they are relatively fast growing bacteria. They don't take much time to grow, whereas methanogens take significant amount of time to grow. And among all these bacteria, methanogens are actually they're known as archaea, but these methanogens are very sensitive. So if you have any issue with toxicity, most affected community will be methanogens. And when you have, like when you get a lot of H2S production, it will affect methanogens activity. So whenever you have inhibition of methanogens activity, you will have accumulation of acetic acid because it will not get used up by the methanogens because methanogens are not active. So when you have this kind of accumulation of organic acid, then that phenomenon is actually known as souring of anaerobic reactor or acidification of anaerobic reactor. That is a common term used to describe failure of anaerobic reactor. So pH will reduce because you'll have a lot of acid formation and accumulation. That is called souring of anaerobic reactor or acidification of anaerobic reactor. That actually talks about the failed state of the anaerobic reactor. So inhibition of methanogens should be avoided. That's why we are using different kind of strategy to get rid of H2S. And within this methanogen community, two different kind of methanogens are there. One is acetate utilizing. Another is hydrogen utilizing.
Sir, you mentioned that methanogens are archaea. So I have read like archaea are extreme living organisms. So like how are that very sensitive?
Yeah, archaea are, yes, archaea are extremely, but that doesn't mean that they're extremophiles. Doesn't mean that they couldn't be sensitive. Extremophiles can grow in extreme environment, but few extremophiles could be very much sensitive to environmental parameter while they grow. And methanogens actually comes under that category. Their growth rate is very slow, and they are also very sensitive to certain parameters.
Okay, sir.
Now, two different kind of methanogens we see. One is acetate utilizing, other is hydrogen utilizing. And hydrogen utilizing methanogens are comparatively more resilient or more robust compared to acetate utilizing methanogens. But anyway, the combination of these two will actually show the performance of the anaerobic system. Now, USB reactor is one of the most widely used anaerobic reactor for treating different kind of wastewater. So in India also, blindly, initially they plan to have this USB reactor installed to clean Ganga river. And Ganga Action Plan and Jamuna Action Plan, they have installed few USB, but their calculations were not correct. The engineers, those who actually calculated or estimated the usability of reactor, that estimate was not correct because the wastewater strength was not good to use them in this environment. So those reactors, wherever they installed as the part of Ganga Action Plan and Jamuna Action Plan, they didn't perform well. Ultimately, they failed. So we mentioned that for running this kind of reactor, you need to use high strength wastewater, or at least carbon content should be sufficient enough to sustain the biomass. So what will actually happen if you have really very low carbon content? All this organism will actually undergo starvation. And in USB reactor, I mentioned that these granules are self-immobilized granules. All these granules are self-immobilized granules. Now, whenever you have starvation, the bacterial biofilm present in the granule will die, and then disintegration of this granule will start. So essentially, if you have low carbon content in the wastewater, you will not have good granule formation, or also you will have loss of granule stability. So disintegration of granule result in the instability of the system, or you can say removal of the granule. And whenever you have removal of the granule, if you get this granule disintegrated and dispersed in the liquid, they will actually go out along with the final water. So that exactly happened in all the failed reactor system where carbon content was less and also the systems were not monitored properly. So there they observed granule disintegration and failure of the reactor system. Ratnesh.
Sir, I just wanted to know that, like, in our department also, the research is being done on Ganga Action Plan. I wanted to know that.
Yes, yes. I think we still have 2-3 minutes to cover that. So this is all about USB reactor. Now USB reactor, another major drawback is the outflow velocity we maintain in this reactor. So we have mentioned that this reactor is a moving bed reactor because you maintain outflow velocity in the range of 1 meter per hour or less than 2 meter per hour. That is the outflow velocity you maintain to just lift the entire biofilm layer or blanket. So it will look like a moving bed reactor. The bed will just move up and then again come down. So this low outflow velocity is not very good for effective mass transfer, because in fluidized bed reactor system, you just disperse all molecules or all granules inside the reactor. So you will get more contact. So interaction will be much more frequent and much more effective. So you'll get higher conversion also. So another option to go for anaerobic system is to go for fluidized bed system. So you just maintain little bit higher outflow velocity, like in the range of 6 to 8 meter per hour, and you get substantial mixing. So it is in USB safely we actually maintain less than 1 or less than equal to 1 meter per hour. And this is for fluidized bed reactor. Now, when you try to increase the outflow velocity, you also incur a lot of pumping cost, because this outflow is actually contributed by the pump. So if you need to maintain this high outflow velocity, pumping cost will also increase. And USB reactor or this anaerobic reactors, they are very big vessel. So you actually put a lot of energy to pump the liquid. Now, another problem with fluidized bed reactor is when you have really very high circulation motion, the bacterial granule will actually have a lot of abrasion between granules. So one granule will just rub the surface of other granule, and then it can create disintegration of granule because of high shear present in the fluidized bed reactor. And also when you have disintegration of granule, the smaller granules, even initial stage, it will actually have smaller granule, then on top of smaller granule, the layer will increase, and then you will get the bigger granule. But when you run the fluidized bed reactor system, you will always have a tendency to get smaller granules along with the liquid, and that's called entrainment loss. So entrainment loss is more prudent when you use fluidized bed reactor because smaller granule will actually go along with the liquid. So essentially we'll be losing biomass a little bit, but you will get more mixing or much better mixing, much efficient transport, mass transfer or heat transfer, means all transfer process will be much more efficient. So you will get much higher conversion in fluidized bed reactor. So in IIT Delhi, we have developed another reactor called hybrid anaerobic reactor, which actually uses the concept of USB and fluidized bed reactor both. So we have developed a reactor where we can run the system at a little bit lower, because most of the fluidized bed reactor system, they use inert support as the core material, and that on top of inert support, they grow the biofilm. Whereas USB, they use self-immunized granules. So in HAR, we use self-immunized granules, but we maintain fluidized condition by maintaining little bit lower HRT. So the HRT will be almost half of fluidized bed reactor system. So two modification. One is in this HAR, hybrid anaerobic reactor, we are not using a moving bed reactor. We are using a fluidized bed condition for fluidizing the granules, and those granules are not grown on inert surface. They are self-immobilized granules. Upflow velocity is much lower than fluidized bed reactor. So obviously the pumping cost will be half of the pumping cost you generally incur in fluidized bed reactor. And also, as you are using this granular self-immobilized granules, you essentially get good mixing for self-immobilized granules, and you get much higher conversion because in a given volume, wherever you have inert support, the support will also consume certain amount of volume. So for a given granule, if you have inert support, you are losing certain volume to accommodate bacteria, whereas self-immobilized granules, that is entire granule is made of bacteria. So you can get some advantage having self-immobilized granules because the volume is also occupied by, core volume is also occupied by bacteria. So you get much higher density than fluidized bed reactor, biomass density than fluidized bed reactor granules, and also the upflow velocity is less, so pumping cost is less. So essentially, this kind of reactor can give better performance than fluidized bed reactor, and obviously it will give better performance than USB reactor. But catch point is these reactors are actually applicable for high strength wastewater, where the wastewater content should have more than 2000 COD or 2000 BOD, yes, 2000 mg per liter BOD at least. And one of the success story with this particular reactor setup actually exploited in Delhi mill scheme, that in the dairy farm, they used this hybrid anaerobic reactor to treat wastewater, and we got really very good conversion. This is actually talking about fluidized bed reactor, and this is the design of our hybrid anaerobic reactor. So you can see the treatment efficiency here. So the treatment system we designed that has a capacity of 10,000 liter per day. So it is not very big system, but it is a pilot scale system where you can treat 10,000 liter per day. And the residence time, so treatment time was around 2 hours. So that is really fast. Generally in anaerobic reactor, you talk about days. So the residence time was very small, and the inlet COD was 1200 and outlet COD was 1100. But again, if you have, but finally that system failed because they couldn't provide sufficient amount of wastewater having good carbon content. So all these reactors are good if you, unless you don't have problem with the carbon content in the influent. If you actually provide very diluted wastewater having less carbon content, then the system will fail. You will not be able to sustain, the system will not be able to sustain for a long period of time. So I'll just share the entire slide because for the last 2-3 classes we have discussed about this, and then you can actually get all the data or all content. Anybody has any question? Fine. Today also I could see only 15 students in the 15 or 14 students in the class. That's okay. So next time onwards we'll see how to improve it. So we'll have, I need to take 2 extra classes that we'll do sometimes next week or next to next week. Yes, please.
Okay, sir. Like I was asking about the books. So books you have mentioned in last slide, right? Last
Yes.
slide.
Yes.
Okay.
And sometimes you may not get each and every details in the book because obviously textbook will actually give emphasis on specific process and they'll highlight few things. So in the class we'll discuss certain things in more elaborately. So obviously, and whatever discussion we are having, I'm not reading only one book. I'm just having, I read multiple books, not only in bioprocess, in other areas also. And from there we are just delivering things. So you don't expect that each and every topic will be covered by any of these books. Anybody has any other question? Okay, then I'll stop here and we'll see you again on Tuesday.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.